the liquid form. But it's more like empirical. It's not like a real relationship. Okay? So, now we go to another topic. How do we decide the crystal structure? Okay? So if you have a metal, say for example, it could be semiconductors, like titanium or something else. How do we decide which one of that one? Okay? So, to decide the crystal structure, think about that. That's a general rule. If we want to interrogate this kind of a periodic structure, when their lattice space is so small, we know that the lattice space in the crystal, because they are atomic crystals, right? These are atoms. See, for example, think about iron. The iron diameter of the iron atom is only about a few angstrom. Same thing for their interatomic space. So if you want to explore the structure with this small interatomic distance, we need something that can see this small distance. Or that means we need to use some way, or use some method, or use some, approach that can have the length scale as small as the interparticle distance. Okay, only when you get that small, you can explore their structure. Okay, same thing, if this kind of a row is really scalable. Later on, if I have time, I will show you some other examples. See, for example, my labs, we are working on much larger particle packing. Those are like a 300 nanometer or few micron size. Okay, to explore the structure of those larger particles is much easier. Okay, because we can just use the light. The visible light has a wavelength about a few hundred nanometers. That's the same size as a particle or the interparticle distance. So therefore, the golden rule here is, if you want to explore this kind of a crystal structures, you need to find something that has a similar length scale as a interparticle or the interatomic distance. Okay? So therefore, if we want to explore the crystal structure, the atomic crystal structure, we need some way. Indeed, later on we found X-ray is a good one. Because X-ray, their wavelength is perfect. It's similar to the diameter of the atoms, right? So, indeed, X-ray could have wavelengths from 0.05 nanometer or 0.5 angstrom to 2.5 angstrom. 2.5 angstrom is very close to most of the atom size, atom diameter, okay? So or sometimes we call this kind of a long wavelength X-ray, we call it soft X-ray, right? So to generate X-ray is not that hard, especially in the current days, okay? So you use a filament, usually a tungsten filament, that can, when you heat up that one, that will generate electrons, right? Hot electrons. These high energy electrons can bombard a metal target. Usually, in current days, we use moly or use copper, okay? So as a target, and then when the electrons bombard these atoms, they will remove the electrons from the inner shell. Okay, remember the quantum numbers when we talk about chapter 2, they could remove the electrons in the n equals to 1 electron. So that means the most inner shells, the electrons in the most inner shells. And then when the electrons from the inner shells are getting removed, the electrons in the outer orbitals of the atom, of the moly or copper, can go back. When they go back, they emit X-ray. Okay, then the emitted X-ray can go in through a window, and then that one can be shining onto your sample you want to analyze. Okay, so this is the way for generating the X-ray. And one example, as I mentioned, one commonly used sample, we use moly, and when you shine the electrons on moly, you could get K alpha and K beta X-rays. They have well-defined wavelengths, okay? That wavelengths actually depend on the energy difference between n equals to 1 for the K alpha actually is from n equals to 3 to n equal to 1. K beta, no, that K alpha is from n equal to 2 to n equal to 1. K beta is from 3 to 1. So that means this one, K beta energy, X-ray has a higher energy. Okay? And so using that one, don't forget, okay, the K alpha X-ray from the Male actually is 0.7 angstrom. So that's a good size, okay? The thing is, when we use X-ray diffraction analysis to decide the crystal structure, the reason why we can use X-ray to explore the crystal structure is very easy. In physics, you guys should know about that already, right? Like the reflected light, right? So when we have this kind of a crystal parallel plane, here we showed HKO planes, they were parallel. When the coming light, or in this time actually X-rays, because they have wavelengths, don't forget, these wavelengths of the X-ray need to be comparable. Their dimension need to be comparable to the interplane distance you are going to explore, right? So in this case, if the X-ray gets reflected from the different HKL crystal planes, the reflected X-ray will interact with each other, right? So don't forget, X-ray is a wave. Okay, so they have wave properties. If they are in phase, this one shows they are out of phase. So out of phase means they will cancel each other. Okay, so when they have the different phases here, then they will cancel each other. You will not see a strong reflection when you see under this direction. Okay, but if the conditions, or that means the wavelength of the X-ray that matches the interplane distance, what you will see, the reflected X-ray, they will be in phase. In phase means they will enhance each other. They will undergo resonance, right? So therefore, you will see a very strong reflection beam, okay, at the same angle. So here, one thing you need to remember, we need to define the incident angle. Incident angle, we define that one as the direction of the X-ray with the direction parallel to the crystal plane. Okay, so that means from here to there. We call this angle theta. Okay, when you say the reflected light at the same theta angle, if the constructive interference occurs, that means the reflected X-ray are in phase, you will see a strong reflection. Otherwise, if they're out of phase, you do not see a strong spot there. Okay, so this is the principle. Okay, then we can get quantitative relationship here. Okay, very easy to calculate. If we think about the two plane, okay, the neighboring two plane, suppose the angle, the incident angle is theta. Okay, and we also know that the light difference, or the pathway difference between Re1 from the top HKL plane and Re2. The only difference, the length of the pathway difference between these two X-ray travel distance is this part plus that part, right? This will be the difference. Okay, so MP is easy to calculate because MP equals to what? MP equals to, if you think about this right triangle, equals to OP. OP is the interplane distance, right? We call that the DHKL. Okay, that DHKL times what? Times sine theta. Don't forget, this one is also sine. This angle is also theta as the incident angle for the X-ray. Why? It's because, think about that. This line perpendicular to this line. This one perpendicular to what? This line is perpendicular to this and that, right? So when the two lines of the triangle perpendicular to each other, their angles are equal. So therefore, this angle equals to theta, right? so this distance equals to dHKL times sine theta. The difference will be twice of that one, right? Because this is one and then this one equal to each other. So therefore, the distance we get is this, right? So when the constructive interference occurs, we know that the wavelength of the X-ray times an integer, that could be 1, 2, 3, 4. Okay, but they need to be an integer here. And lambda should equal to what? Should equal to the distance difference between the ray 1 and the ray 2, right? So that difference is, we know that it's 2 times is coming from 1 and 2, right? 2 times the DHKL is the distance, times sine theta. Okay, so if a condition matches here, we know that this one we know is called the Bragg law, right? Or Bragg's diffraction law. So it's widely used, not only for the X-ray analysis, but also for whatever size if the diffraction occurs. Okay, we can always use this diffraction law to describe that. Okay, so here, one thing important here is, first one is a number, it's an integer. Could be 1, could be 2, could be 3, right? That means we call that diffraction orders, right? Lambda is a fixed number, right? Because when you try to do the crystal analysis, you just use one X-ray. Usually you just use one X-ray, right? See, for example, could be moly K alpha or could be copper K alpha line. Okay, so just give me. So lambda is a fixed number that determined by your equipment. Okay, DHKL, usually that's a fixed number if kind of like you know the crystal, you know their crystal orientation. Theta is angle of the incidence, right? So by using that, well, we can easily, if we know the lambda, we know, say for example, theta, we can easily decide DHKL. Once we know DHKL, because HKL are the crystal number, are the, remember, related to the Miller indices, right? If you know HKL number, if you remember the equation as I showed you before, this one, next one. Okay, if you know the DHKL, because you know HKL number, then what we can decide? We can decide the A, the lattice constant. Okay, that's usually the way we do. Okay, so therefore, if we want to know the crystal structure, we usually use an X-ray, use a Bragg's law to first decide the DHKL. Once we know DHKL, then we can back calculate the lattice constants. Right? Okay, so there's a question there.
So what is the order of diffraction?
The order of diffraction is this, okay, is, it depends on the orientation, okay, it depends on how to see that, okay, how to see clearly.
Is it electron configuration?
No, it's not related to that. It depends on, let me give you a better explain on that one. Did you guys know about the small hole diffraction? Remember that? When you have a hole, when you have the light coming in, when the light had the wavelength of the light is similar to the diameter of the hole, right? So what you will say, you will see the light will not go directionally going onto the screen, right? You will see those kind of rings, right? For those of the rings, you know that immediately to the center of this hole is very strong, and then they gradually decrease, right? For those of the decreased lines, those should be the higher orders. So therefore, for those kind of higher and higher orders, they will be at a different location, but their intensity will be greatly reduced. Most important, so we will consider for those kind of a small angle or small hole diffraction, we only care about perhaps the most centered one. The most centered one is the zeroth order, or the nearby ring. That could be order 1 and order 2. Okay, I hope that one can be easier to understand. But don't forget, for satisfy this Braggs law relationship, okay, the n could be just n could be 1. So that means one wavelength difference that could equal to this. But that's not the only thing. It could also be 2 times of wavelengths. When they match this condition, they will also get the same interference effects. Yes.
So do you get more interference from the diffraction or from the whether the wave hits the top of the crystal in phase and the reflection interferes?
It's mostly coming from the interference effect. So the match of the, think about that one. Suppose n equal to 1. How about that? Okay, when you know the wavelengths, you can easily, and also when you fix the angle, you will know about the DHKL. Or that means usually what you do is you try to explore. Suppose a wavelength is a fixed number. Suppose a DHKL is a fixed number also. So that means you have a crystal has a, say for example, 111 plane there. Okay, if you want to match this condition, what you will do, you will change the detector position, right? Until you, perhaps at a very low angle, there's no reading because there's all the reflected light get canceled there. But when you move that one across at a certain angle, at that angle you will see a very large reading. Okay, it's a beep, that will give you a very sharp peak. So that indicates at that angle that matches this Braggs law. Okay, so that one, yes.
So this is used for like large molecules like proteins.
That also works, yes.
How does the math get computed? It happen in so many different combinations of ways, or was it characteristic at this point?
For the protein X-ray analysis, usually because the molecules are much larger, right? So it could be the nanometer scale, or could be even larger than that one. You usually cannot use like moly or copper. First reason because they are too energetic, too much energy. They will burn the proteins. Okay, so usually you need to use soft X-ray. Very low wavelength one, they will explore those kind of a large protein structure. Okay, so or another way to do the largest structure. Okay, one way to do is using the longer wavelengths. Can you guys, that's a very good question. That helps us to understand the Braggs law. Besides that, if we want to match this Braggs law condition, one way for the D, suppose the D is very large here. Now we are talking about the nanometer scale. 1 order of magnitude larger than the typical atomic crystal. One way to do is use a larger number. What else could we do?
Smaller.
What else? Suppose we still want to use our, my lab, we do not have those kind of a soft X-ray. But I just have a copper or moly. What else we can achieve? Yes?
You can change the angle?
Yeah, you can change the angle. For those larger ones, do you need a small angle or you need a large angle? Suppose number is a fixed number. Small angle. So we call that small angle X-ray. Okay, or we call that SAX. So it's a widely used technology here. Okay, so it's called small angle X-ray analysis. So in that case, or using the small angle X-ray analysis, we can even explore like hundreds of nanometers here. But the angle need to be very small. Need to be 0.0 some degree. Okay, yes.
When this is done like computationally,
Mm-hmm.
do you approximate sine theta with theta, or is that unnecessary?
It's much more complex than what I described here. This is just the very basic. As I mentioned, the crystal analysis is a whole class. It's perhaps one of the most difficult classes in material science. Okay, many of my students failed that class. They got the D. It's not an easy class, is it? It's a lot of, it's one whole year information there. Okay, but anyhow, we do not have time to, yeah.